Hello everyone, and a very warm welcome to today's PV Tech webinar in association with Kontron AIS and ISC Konstanz. My name's Ben Willis and I'm consultant editor at PV Tech. Today we're going to be exploring the role that manufacturing execution systems can play in helping PV producers ramp up wafer and cell production in the new gigawatt scale factories needed to support solar deployment over the coming years. Since the early 2010s, China has become the global leader in PV manufacturing and now enjoys the informal but undisputed status of PV supplier to the world. Yet momentum is building for PV manufacturing supply chains to become more locally specific to the end markets that they serve. Producing wafers, cells and modules in the geographies where they will be consumed would ensure greater energy independence for the markets concerned and offer other benefits such as greater supply chain transparency and better control of the carbon emissions from production processes. Initiatives such as Joe Biden's Inflation Reduction Act in the US and the Net Zero Industry Act in Europe are just two examples of the efforts being made to boost the local production capacity of renewable energy technologies. Other regions such as MENA, India and Australia are also likely to become increasingly important manufacturing hubs, serving planned deployment in local markets. But while the future production landscape looks set to be less centralized than it is currently, for the new companies that are likely to emerge as a consequence, ramping up production to compete with established players poses a number of challenges. This is particularly the case given the complexities of modern PV production lines that must balance volume production against the need for high quality end products. One key challenge for manufacturers is gaining the necessary visibility on new production lines to mitigate any process deficiencies. This is where manufacturing execution systems come into their own, offering a powerful tool for acquiring and interpreting data across multiple process steps. They enable the entire process flow for individual wafers to be traced and controlled. So today we're going to learn just how valuable a tool these systems can be in aiding the rapid ramping of solar cell production. And to guide us through the topic, I'm delighted to welcome today Frank Tannhäuser, Senior Sales Manager, Manufacturing Automation of Kontron, and Jan Lawson, Deputy Head of Solar Cell Research at ISC Konstanz. After Frank and Jan have given their presentations, we'll be opening the floor to you, our audience, for any questions you may have. As always, this interactive part of the webinar is really important, so please take the opportunity to put any questions you may have in the questions tab at the bottom of your screen, and we'll do our best to put them to today's speakers. So without further ado, I'd like to hand over to Frank, who will be kicking off today's webinar. So Frank, the floor is yours.
Yeah, thank you, Ben, and everybody for joining the webinar and your interest in ramping up solar cell production with the process knowledge from ISC Konstanz and the help of Kontron Tab Eagle MES. Last week, the latest ITR PV report came out with updated trends and numbers. The trends have not really changed. The direction is still the same, but the impact on the ramp-up phase of solar cell production becomes more and more important. And we are seeing now over 50% of production sites will be greater than 5 gigawatt in 2024 already. And more efficient machines with higher throughput are introduced into production. And cell technologies change also to more complex technologies like IBC or TOPCon, which has a share of over 50% already now. And this creates even higher hurdles for the ramp-up phase. And we want to show through the webinar how we can address these things, for instance, with smart automation solutions like MES. And this leads us actually to our first question for our audience. We have prepared some polls during that webinar, and we would invite you to answer these polls. And you can please click on the polls section in the right bottom corner of your screen. or you will just see it in the middle of the screen now. And the question is, are you planning to build a new factory with smart automation capabilities? And please answer yes or no. And we will see the results in the polls tab if you go there. I'm waiting for some more seconds. But the trend looks like that most of our participants are planning to build their next factories actually with smart automation capabilities. And that's good news. And that's the topic of our webinar. And I hope we can convince all other people to also start building factories with MES and all the new possibilities we have. Okay, let's have a look at the agenda. Our agenda includes the following topics for today. We will start with an introduction of ISC Konstanz and its services. Jan will then tell us about challenges he experiences during process optimization and show examples of tracking methods and their limitations during ramp-up. And after that, I continue with an introduction of Kontron AIS and FabEagle MES and give detailed information and some examples about the benefits of MES and single wafer tracking. And now, Jan, the stage is yours, and please go on with your introduction.
Yes, thank you, Frank. Hello, everybody. Let me introduce first ISC Konstanz. The International Solar Energy Center Konstanz is an independent non-profit association based in Germany. We have been founded in 2005. We have a team of 65 employees from 20 different nations, so a truly international team. And our main scope, of course, is research and development on crystalline silicon solar cells, modules, and energy systems. But further, we can also provide to our industrial partners training and education, material testing, proof of concept, and pilot production. In our lab, you see below, we have a clean room and a fully equipped pilot line for solar cells and modules. And we also offer technology transfer and consulting at the customer side in your factories. Here you see a brief overview of our roadmap. So on the left-hand side, the TOPCon solar cell and the Zebra IBC solar cell, both are fully developed and ready for transfer. Actually, both are already in production with efficiencies above 24%. And for both of these solar cells, upgrades are in development in our lab. So for the TOPCon cell, we are developing passivating contacts on the front side, which are expected to raise efficiency at least by 0.5%. And for the Zebra IBC cell, we are developing passivating contacts for both polarities. And this will bring a solar cell with more than 25.5%. We have more than 15 years experience in the development and in the industrialization of solar cell concepts. Our focus was always N-type solar cells. Below here, you see a list with successful process transfer and ramp-up projects of the last 10 years. So in total, we concluded 7 ramp-up projects in different regions of the world. We do offer a full range of services regarding technology transfer. We can help already during selection of the technology and selection of the equipment, preparation of the manufacturing site, the transfer of technology involving training of your personnel, and then during the ramp-up phase, we can support both the ramp-up on the floor, but also documentation and quality documents, market integration, data sheets, and so on. And this can be extended to further continuous improvement and integration of upgrades. Today, we want to speak about process optimization, which is an important part in all of these three sections. We typically apply DOE-based process optimization. This stands for design of experiment. This is an empirical method for process optimization where we intentionally vary the input parameters and observe the effect on the output parameters. You see this here schematically in the graph where we have a PCVD system with two knobs on, and by turning the knobs of this PCVD system, we observe the changes which it causes to the peak and to the width of this VOC distribution on the right. In reality, of course, it's more complicated. We have many input variables in the process, and we also have many output parameters. And this requires an educated turning of knobs and the use of statistical data analysis and physical models for the interpretation of the results. Nevertheless, the important part is we need a correlation between the variations in the process and the final results to draw conclusions, here displayed by this arrow. What new challenges do we have with process optimization? First, I would like to mention we have long feedback loops for a lot of parameters. On the left-hand side, you see an example with a short feedback loop. So in an emitter diffusion, if we change the temperature during deposition or drive-in, we can measure the result of this directly after the diffusion on the sheet resistance. But if it comes to other parameters, as for the minority carrier lifetime, for example, a lot of processes play in there. And here, for example, if we displayed the TOPCon manufacturing sequence, and if we have contamination by insufficient cleaning in this very first process step in the texturing, we will not be able to see it in any parameters. The wafers just look the same through the whole process sequence, and reliably, we can only measure it after the last PCVD step. So right at the end of this process sequence, or we can, of course, see it in the final IV testing. So there's quite some time shift between the process variation and the result in the measurement parameters. A second challenge are more sophisticated cell structures. On the one hand, the process sequence gets longer. You see here displayed 3 examples for process sequence with more and more process steps. On the other hand, the more sophisticated the cells are, the more sensitive they also get to misprocessment, I would say. So as an example here again, the minority carrier lifetime. If we have a cell with more than 24%, we need a much higher lifetime to reach the full potential of this solar cell structure. So in this small graph here, you can see in red a cell with just a mediocre passivation on the rear side. So this cell reaches or saturates already at 0.6 milliseconds lifetime, while the TOPCon cell, which has a potential to go above 24%, also needs a much higher lifetime to reach its full potential. So it saturates above 3.2 milliseconds only. A further challenge are the bigger fabs and the higher throughput of the tools. As Frank explained, the factories are getting bigger. 5 gigawatts is just the standard size now. This means we have a lot of parallel tools which are clustered and which are served according to their availability, whether by human operators or by AGVs. These tools are also not matched in tool throughput or in batch size. So, for example, here are written the batch sizes for diffusion, wet, and PECVD. And if you try to find the least common multiple of these three numbers, you come up to a very high number, which means that actually you cannot speak anymore of production lots which travel or which have the same history in the factory. But in each tool, the wafers are clustered in a different composition together to batches. And this makes it very difficult to know which tool is producing a bad result. The single tools also get bigger. This also means a challenge. On the one hand, my observation is the batch size is increased further and further until finally homogeneity becomes a problem. You see this PECVD board here. It started with 144 and it has grown to 640 wafers now. And now we see that the first and last positions of the board, we get problems with homogeneity. And last but not least, the tools are not optimized for tracking, but the tools are optimized for maximum capacity. Many of the tools today use buffers. This is very good to reduce interruptions in the process flow, but it's not good to follow the wafers. So here on the lower right side, you see a graph where we have taken 300 wafers and marked them with the code, and we put them in the printing line with 3 buffers. And you see in which order these cells here come out of the printing line. Yeah, so it's not a clear sequence, but it's always interrupted. So if the first in, first out principle is not followed in the systems, really complex mixing patterns involving many hundreds of wafers are created. This becomes even worse if tool have parallel lanes, which is displayed here in the next picture. Here, this is a loading unit of a PECVD tool, which loads wafers from 2 lines of carriers. And each line has a possible to reject wafers, to buffer wafers, and finally stacks them in this loading unit. And the gripper selects from whatever lane is ready first. So this is good for throughput, because if one line is blocked, the other line keeps working and we don't have interruption for the gripper. It can always grip wafers, but it's just a nightmare for tracking these wafers. So, which brings me to manual tracking methods. How, with so many challenges, how is material tracking possible at all, you might ask? We have some tricks, which I'm going to show you. The first is very easy, physical marking of wafers with a diamond scriber or with a laser. The advantage is we have really reliable information. The disadvantage is it's really a very time-consuming effort, and it's also difficult to find the wafers back between 10,000s of produced wafers per day. Second possibility is to use carrier-wise tracking with 100 or several hundreds of wafers per group. The advantage is you can try a lot of parameter variations, you can have a lot of split groups, but it's very difficult to avoid mixing. So with substantial effort, it is possible. You need a person to follow the material. You need to empty the automation of the tools before you come with the material. You need to block buffers and parallel lanes, and then you can manage to get the material through these tools. But doing so, you are also discontinuing your production flow, and this might influence the outcome by itself. And last possibility would be to go with bigger batches. I call it trolley-wise tracking, so with 1,000 wafers or even bigger groups, 10,000 of wafers. So here the chance to get mostly correct information is much higher. The middle part of the batch is mainly mixed within itself, and only at the edges of the batch we have mixing with neighboring groups. But you can only test a few variations. And still the effort for tracking is high. And if you are too daring and if you try unusual variations, you might also produce a lot of underperforming cells, which will not make your production manager very happy. So I would say with an experienced team and skilled operators, all these methods are possible, but none of these methods is really fun. And this brings me to my summary. ISC can provide technology transfer and ramp-up support. DOE-based process optimization requires the correlation of process parameter with final cell results. However, several factors made it more difficult to track material over the last years. Manual tracking still is possible, but it's a time-consuming and a resource-consuming endeavor. If somebody screws the tracking, it might lead to ambiguous results and make frequent repetitions necessary, or it can even lead to erroneous conclusions. And with this, I would like to hand over to Frank, who will explain us how MES software can provide relief probably to these problems and support material tracking.
Okay, thank you, Jan, for all the detailed information about challenges in ramping up solar cell manufacturing. And I want to continue with some information about Kontron AIS and how FabEagle MES extremely helps during ramp up and also during the operation of a cell production line. First, some information about our company Kontron AIS. We are in the business for over 30 years now and are working in PV for over 20 years. And besides PV, our projects are mainly in the semiconductor and similar industries with discrete manufacturing requirements. Besides customer projects, we are also developing software products. There are products for production control, like the FabEagle MES we are talking today about, but also for connectivity and monitoring. Equipment automation software like Tool Commander or FabLink for semi-compliant automation are also part of our portfolio. During the last 20 years, we have installed over 80 MES systems for ingot, wafer, solar cell and module production across the world. And currently we are deploying mainly MES for solar cell and solar module production. And yeah, like I said, we are building production control systems for PV manufacturing for over 20 years now. And we have addressed the needs of our customers by constantly innovating our software technology. Requirements are addressed in 3 focus areas, which demand attention to secure quality, improve processes, and save costs in PV production. The first area is transparency. It's all about to see what's going on in the factory, how to reduce downtimes and time for troubleshooting to optimize production. Motivating employees with feedback, for example, on the progress made to fulfill work orders is also part of transparency. The second area is traceability and how it helps to improve product quality by collecting material batch information of consumables, for example, and related process and quality data. All the things that happen to build a product, and this is exactly what is needed to accelerate ramp up of a factory. And the last area is production control, and it includes everything needed to set up a production with production orders, work plans, bill of material, statistical process control, and event management. And these three areas of functionality lead us to the next question to our audience. And we have prepared the second poll, which should come up immediately. And the question is, have you ever considered the use of an MES to improve traceability. And yeah, you have three answers. I already have an MES for traceability, would be one option. Second option would be I plan to use an MES with traceability. And third option is I don't need traceability in my factory. And yeah, please submit your vote. And when you go to the poll section, you will see the result. And yeah, it's still counting. It looks like currently that most of our people in the audience are planning to use an MES with traceability, and that's actually good news. And that's also what Jan showed us during his presentations, that it becomes more and more complex to ramp up a production without traceability and without an MES system. So it's a quite impressive result that we see here. To support the previously mentioned traceability, transparency, and production control with MES, interfaces to production equipment and IT systems are most important to connect and enable the data flow. For this purpose, an integration layer is needed, which we are providing by standardized software, for instance, called FabEagle Connect. It makes it easy to connect to equipment, transport systems, quality control, and measurement devices. Additionally, connections to ERP systems or for order management and interfaces to cloud solutions are becoming more important. And this slide shows an overview about the important software modules that we have available today and which are helping to ramp up and run a factory for PV production. We are concentrating today mostly on the parts which will help for single wafer tracking, and the most important modules for that are the order management, work plans and recipes, and with all the bill of material information. And then, of course, material tracking, as well as the machine process quality data acquisition modules to collect all data while the workflows are executed. And this data is used to enable production control for the growing throughput and volume within factories, like we have heard before from Jan. And to make all the MES functions available, we implement these mentioned software interfaces to connect to machines and metrology equipment. And this slide shows which data and events MES exchanges with equipment and is needed to make material tracking work. And this applies to solar cell and similar, also to solar module and ingot manufacturing as well. There are information about the process material, process start, complete timestamps, and all the related process and quality data. And material can be either tracked physically with laser etched data matrix code, for instance, or by tracking RFID marked carriers with the cells in it through production. And in this case, there's no physical identification on the product. The solar cells are tracked by evaluating all the movements of these wafers through equipment, and this is called virtual wafer tracking. And it can be done in wet chemical or deposition processes, for example, but also for any other process. And it's one of the key advantages and functions of our FabEagle MES system. I now want to go a little bit more into details and some examples how this virtual single wafer tracking helps during production. But first, an impressive chart. And in this chart, you can see the variability of wafer movements between individual machines based on data from a sample cell factory. It starts with the commissioning of wafers, and we have a wafer inspection, texturing in this case, and we have PCVD and PVD equipment, and finally printing, laser cutting, and IV cell tester sorter. And additionally, within an equipment, parallel processing areas like lanes or process chambers can exist, and which makes it even quite more complex, like Jan showed before in his images. And just consider some of the routes through production in this chart. Just the pure number of machines and metrology equipment is adding a very high level of complexity during the ramp-up of production and later on during the operation of a cell factory. And connecting all the information of these machines and equipment back to a single wafer can only be managed by single wafer tracking and an MES. And back to the topic about how to improve cell efficiency by using virtual wafer tracking during ramp-up. The improvement can be shown based on data from a past project where one factory was running for a couple of months with an only partially working tracking system, and then we worked to improve it. And you can see in the graph on the left side, by constantly increasing the cell tracking rate, which is actually the green line, the cell efficiency increased in a short time frame, because the collected data together with single wafer tracking was used to analyze and optimize production much faster. And at the same time, the deviation of the efficiency was reduced, which can be seen in the right graph. And this is, I think, an impressive result. And the factories that are using this tracking technologies today do definitely have an advantage. Here on this slide, I want to show 3 more examples how MES and single wafer tracking information can be helpful during operation of a cell factory. The first, on the left side, you see that electrical measurement results from the IV cell tester sorter at the end of the line can be mapped to any location or position in production and used to visualize and analyze the influence of the processing location or specific equipment to the cell efficiency or any other quality information. And this can be done, for instance, down to the slot location in a wet bench carrier or to the location in a process tray. And second example in the middle, besides the measured quality data, other information like EL images can be used and mapped to locations within processes. And what you see, for instance, in the picture in the middle indicates a potential future hardware defect, which can be avoided easily by a preventive maintenance. And the third example on the right side is about connecting the IV data like color measurements with the lifetime information of a magnetron, for instance, which is needed for sputtering processes in PVDs. And reaching limits for certain quality measurements may result just in scheduled maintenance tasks, which can be planned closer to the end of life of certain spare parts. And this is possible by using the quality data that is associated to every single wafer. And this all eventually saves costs and improves product quality. I have a final summary slide about the benefits of single cell tracking. First of all, it enables rapid ramp up with maximum efficiency because of all the collected data that we have available in our database or any other data lake architecture that we can provide. Second, we need less engineering staff and less test wafers are needed thanks to the automatic data collection already during ramp-up phase. And finally, good tracking during ramp-up phase allows a more complex design of experiments with conclusive results, which is also helping Jan during his optimization approaches. And then we have a second group of benefits after ramp up during the operation phase. If you think about process improvements, they can be evaluated and introduced much faster because of the available data. And automatic detection of equipment malfunction or scheduling of maintenance tasks can be also done with this data. And that's also an example that I showed during the webinar. And last thing is, even the identification of root causes for product defects is possible much faster due to all these collected data. We have one final poll before the Q&A session, and the question is just, do you see advantages in using an MES with single wafer tracking for the ramp-up and operation of your new fab if you plan to use or if you plan to build a new fab? And answer is just yes, you see advantages of using an MES, or maybe no, or maybe also you cannot say it because you're not planning to build a factory, or we were not able to convince you during that webinar. And in the poll section, we will see the results, and actually looks like over 50%, so 60% are actually seeing benefit of single wafer tracking in an MES for ramp up and also for the operation. And that's very good result, I think. And now I want to hand back to Ben for the Q&A session.
Many thanks, Frank, and also to Jan there for your presentations. Very interesting indeed. Thank you both. We don't have a lot of time, but we've got a few questions here to get in. I guess one here for Frank about the sort of optimal moment to start selecting a solution such as the one that you've just outlined. I mean, for people setting up new factories and looking to ramp those obviously as quick as possible, what's the best time in that process to start selecting an MES solution?
Yeah, from our experience, it's, I think, best to start very early. So when you have decided to build a new factory and you start selecting equipment, then it's already a good time to contact your preferred MES vendor, because at this stage already we can provide you documents about the needed interfaces to the equipment, give you some specifications which can be used during your procurement process while you're talking to equipment vendors, and this will make sure that the MES can be connected to the equipment and that we will have a smooth ramp-up phase.
Great, thank you very much. And one here, I think probably for ISC Konstanz, for Jan. Can you improve processes and solar cell efficiency also for factories in operation, or do you only provide services like this for factories during the ramp-up phase?
Yes, thank you. Yes, we can also provide services for existing factories. Of course, we are a small institute. We cannot handle too many projects at the same time, but basically just come with your need and ask us, and yes, and we can find a solution.
Excellent, great. Probably one for both of you here. Can the approaches presented for accelerating the ramp-up phase of solar cell production be applied to other areas of PV production, such as ingot, wafer, or module production?
Yeah, maybe I can start first. Yeah, currently we are doing most of the project in solar cell and solar module production. We can also support the ingot and wafering areas, which are quite similar regarding tracking. It's not wafering, it's not an assembly process. It's more a process where you divide one material, which is an ingot, into several wafers. So this is actually the different approach, so not assembly, so it's kind of a disassembly, I would say, but it includes the same functionality, so collecting data, tracking material can be attached to carriers, similar thing in ingot area. There's preparing the silicon charges, loading the furnaces, monitoring the CZ growing process, supporting the cropping area, and tracking all the related data back to the original silicon. And that's also possible in the MES, and that's also something we've done before in other projects.
Many thanks, Frank. Anything you want to add to that, Jan?
No, I fully agree. I mean, especially with several ingots being pulled out of the same batch, there is interesting quality to track how these ingots later perform in solar cell manufacturing, the upper parts, the lower parts. So there's a lot of data to be correlated with each other.
Very good, thank you. And a question here about the I guess the sort of compatibility of the MES solution. The question is, would the MES solution be compatible with all equipment in the production line? I guess probably Frank, that's mainly for you, but maybe Jan, you'd have something to say about that as well.
Yeah, that's actually a good question. And what we have experienced in the past is that that's part of the project to work together with the equipment vendors, together with the end customer who's then producing basically the solar cells. It's an effort of Kontron AIS, the equipment builder, and the end customer who's building the solar cells to work together to establish these connections. We have a standard here especially for solar cell production is a PV or semi PV2 standard. Most of the European vendors and also vendors from Asia are supporting the semi PV2 standard. That's a standard which is derived from a semiconductor standard, and all the equipment that is supporting SECS GEM or PV02 can easily be connected to MES. We are also working with customers or machine vendors who want to provide an OPC-UA interface or even TCP/IP or direct PLC connections. So we are very flexible regarding interfaces, and we are happy to talk to machine vendors to connect to the MES system and establish working interfaces. And like I said, it's one of the major or main parts of such an MES project, connecting machines, the functionality itself in the MES with all the tracking and production control. That's and a standard functionality, pretty similar in every factory. And setting up these connections is the main part of such a project.
Thank you very much. Anything to add to that, Jan? No.
Okay. No, the software part I leave to Frank.
Fair enough. Yes. Understood. Well, we're very much sort of out of time. I just, by way of a sort of concluding question, I guess this is one from me, which I suppose is a bit of a sort of journalistic question, really. I mean, the polls that you ran in the presentations there, I mean, show pretty strong interest in either the idea of using a sort of MES type setup or indeed plans to actually implement one at some point in the future. I mean, I guess, looking ahead to sort of the levels of deployment of solar that are expected over the coming years, and, how the sort of manufacturing end of the industry is going to have to sort of respond to that. I mean, it seems like really this is very much the way things are going to go. I wonder if you could both just give a sort of parting comment on, the extent to which you think, automation, sort of MES type systems are sort of fundamental to, the future of PV manufacturing.
Mm-hmm.
I can start. I think it is the future because we are learning more about these processes. We can conduct much nicer experiments. We can have faster learning rate with good data quality. And especially if you want to set up factories in areas with high labor costs, you want to work with a lower number of personnel and highly skilled personnel. And then this is really a huge help to use software as a help of software. And I think software is getting bigger, faster. Data storage is getting bigger, and this is the future.
Mm-hmm. I can actually confirm what Jan is saying. I completely agree to that. We are seeing bigger factories with automated transport systems, full automation, and somehow you need to control all these machines and make sure that the quality is right, that you have the possibilities to optimize your production, and everybody wants to use the new technologies that are coming up regarding artificial intelligence and so on. And all these things are relying on the good data quality, and this can only be supplied by something like an MES with direct connection to every machine, and which is enabling tracking to the whole process chain.
Super. Well, thank you very much. We are out of time, I'm afraid to say. So, that brings us to the end of today's webinar, and I hope everyone who's tuned in has found it very insightful, as I certainly have. Recordings of the presentations and slides you've seen will be sent out to webinar participants in the next few days, and the full webinar will also be available to view shortly on PV Tech in the on-demand section. So keep an eye out for that. If you've asked a question we weren't able to get to today, Frank or Jan will be able to answer those after the webinar. So all that remains is for me to say a huge thank you to our speakers, Frank and Jan, and of course to Kontron, AIS and ISC Konstanz for supporting this webinar. Their contact details will also be available on the presentations you receive. So I hope you will all be able to keep the conversation going. From all of the team at PV Tech and me, thank you very much to everyone for tuning in. Have a very good rest of your day. Thank you and goodbye.